So we were talking about yesterday endothermic and exothermic processes, and you guys were tasked with kind of learning some of that on your own. But I think it was a relatively easy assignment for you to get through, especially since I left you the answer key as well. Up front, yes. Okay, so when we're talking about these, we need to make sure that we understand some of the terms. We can have either heat absorbed, which is called an endothermic reaction. It's entering into the system. Or we can have heat released, which is exothermic. It's exiting the system. And when we talk about that, we need to make sure that we understand what system and surroundings are. So the system is the part of the world that we're studying. It might be the chemical reaction. It's the stuff that is actually reacting, your ice that's melting. The surroundings then is everything else around that. So it's the air. If you touch the beaker, it's going to be the outside of the beaker, your hand. And then the universe is both of those things combined together. Enthalpy then is the amount of heat, not heat that is transferred. And it's just a fancy term that they use for heat. Okay. When we look at heat, we're looking at work that's being transferred between the system and surroundings. So the energy is of the system is the energy of the surroundings, or if no work is done, the heat that is lost is equal to the heat that's gained. The quantity or amount of heat then is typically measured in something called joules or kilojoules. And if thermal energy is transferred from the system to the surroundings, that heat is negative. So this is an exothermic reaction. Then your heat is negative. If it's an endothermic reaction, it's going from the surroundings, then your heat is going to be positive. Work then is that energy that's needed to move something. And typically we see that in terms of gases. We've talked about that and how you can compress gases and then release them. And that is how essentially your pistons work on your car. Okay, you go through these combustion reactions, you generate gas, a gas, not the gasoline, but gas. That's going to compress a piston, and then when it moves up, it's going to generate and turn it into mechanical energy, which then causes your axle to turn, which then turns your tires. All right. When we talk in terms of endothermic processes, that's heat that's absorbed from the system. So enthalpy is going to be positive. Your reactants will have a lower amount of energy than your products. And if we look at the change between that, that is your delta H. Phase changes can also be, it's not just reactions, but it can also be phase changes such as melting, boiling, vaporization, and changes that involve separating of particles, and we'll talk about that in just a minute. Exothermic then is just the opposite. Here, your reactants will have had more energy than your products. And these are your phase changes. We've talked in terms of heating curves and cooling curves. So if it's endothermic, it's going to be a heating curve. If it's exothermic, it's going to be a cooling curve. And then we've also talked in terms of solutions. We talked about solutions earlier and how we have to have a solvent that's going to expand. We have to have a solute that expands. Those overcome their intermolecular forces. And then when they recombine, that's exothermic. If this has more energy than this, then it's going to feel cool to your hand. If this has less energy than this is giving off, then it's going to feel warm. So when we did that sodium acetate and I brought that around and had you feel that, do you remember that? No, did I not do that in here? I'll have to try to get something out for you guys to experience that. All right, so then you had some homework to do last night. You had the answer key to check that. Any questions on the stuff from yesterday? Anything that makes sense? All right, so let's turn our attention. Just can't get rid of that out of my throat. All right, so endothermic and exothermic, when we talk about diagrams, and we've already kind of touched on this just a minute ago back with a previous one. If you want to know what that delta H or that enthalpy of reaction is, you simply find where the reactants are, where the products are, and whatever the difference is between that, that's your delta H. So in endothermic reaction, you're going to have a negative value. I'm sorry, exothermic reaction, you're going to have a negative value. Endothermic, you're going to have a positive value. We could also look in terms of our delta H formation of products and reactants. And we will eventually get to this point. We haven't gotten there yet. This would be 15.8 for you guys. So when we get to our products minus reactants, they give you these values and you simply just have to subtract them. So the sign, again, for delta H is going to be negative for exothermic and positive for endothermic. On the reaction pathway diagram, then, delta H is going to be labeled as the difference between those energies of the products and reactants. And then we have something called activation energy. So do you see how on these graphs you have this big hump, or I guess it's a little hump here, but a big hump here? This is how much activation energy you need to have to make this reaction run. And essentially what that activation energy is it's breaking those bonds or the intermolecular forces that you need to be able to have that happen. So back here when we were talking about these, that's going to be the energy that you need to expand this solvent and this solute. How much energy do you need to overcome those intermolecular forces in order to get these things to combine? Okay, so when we look at these and we have more energy, when we break these things apart, that's going to take energy. They're free here and then they come back together, they give off. This is going to be your energy change. Since your reactants are higher than your products, that means that this is going to be an exothermic reaction. Catalysts simply lower this activation energy. So when we talk about this lowering the activation energy, you actually have catalysts within your body. What are catalysts in biological systems called? Enzymes. Very good. Yep. So you have enzymes within your body that do this. One of the enzymes that you have is amylase, which is in your spit. It actually starts breaking down complex carbohydrates. So if you take a cracker, a saltine cracker, okay, and you put that in your mouth, does it taste sweet? No. You let it sit there and work it around for a couple minutes, and I know you're like, ew, but yeah, it'll start to taste sweet to you because what that amylase has done is it's broken down those complex, that starch, and it's broken it down into simple sugars, which will taste as sweet. I'm gonna try that. Kind of cool. Delta H is not changed in this product because remember process if you use a catalyst, because remember delta H is the difference between your reactants and your products. So this has just lowered the activation energy. It hasn't changed this net energy here. All right, I'm going to do the I do. You guys are going to get together and do the we do when I'm done with the next set of notes. Okay, so I'm going to try to draw a straight line here. Up. I was so close. Yep. I did pretty good going down. That's better. Okay. Kind of petered off in the end, but we're okay. All right, so we have a reaction pathway here. What does this negative value here mean? Exothermic. So that means that our reactants are going to have more energy than our products. And then when we draw this, we need to show some activation energy. And hopefully you can draw a smoother line than I can. I have trouble trying to draw smooth lines with this thing. All right. And then they wanted us to show the delta H here. So remember, the delta H is the difference between my products and my reactants. So this is my delta H. And if they gave us values over here, all we'd have to do is subtract those to be able to get the quantity. Easy enough? They didn't ask for this, but what would this be from here to here? That's our activation energy. Yep. They did want us to label our reactants and our products. All right. So you've got a we-do that you can come together and work on together in just a few minutes. I want to go through this heat transfer then. Heat transfer, remember, is where we are taking energy from a colder thing. So this could be our red line here, could be our thing that's colder, and they've got your temperatures here. So that's a negative 100, and something that's warmer. So if we put the colder thing with the warmer thing, what's going to happen in terms of thermal energy? Take your hand and put it down on your desktop. How does it feel? Cold. Why? No, the desk is not cold. What's happening?
My hand is transferring energy.
Right, your hand, the heat from your hand is going into the desk. If you leave this sit here for a few minutes, what's it going to feel like? Yeah, it's going to feel the same temperature because you've reached what's called thermal equilibrium. Only heat moves. Cold does not move. Okay? So in the winter, when you open up the door and your mom's like, "You're letting the cold in." Yeah? No, you're not. What are you doing? Letting the heat out. Now, I do not advise you to say that to your mother because you might end up with a backhand across your face. But that's the truth. Okay? Because only heat moves. Heat moves in 3 different ways. Conduction, which is what's happening with your hand here. Okay? Convection, which is what you see as like steam coming up from a boiling pot, or radiation. Where do you get heat from radiation? Sun. Okay? Sun has heat energy that it's radiating to us through empty space. So that's radiation. Okay? So when we're talking about aluminum here, we've got aluminum. This aluminum is at 85 degrees Celsius. So we've got aluminum and we have water. So what's happening in terms of the water, which is at 25 degrees Celsius, we're putting the aluminum in the water. What's happening to the temperature of the aluminum when I put that aluminum into the water? Yep, that's going to decrease. What's going to happen to the temperature of the water? It's going to increase until they reach what? Thermal equilibrium. What's happening in terms of the average kinetic energy of the aluminum?
Also going down.
Yep, it's going to go down. What happens to my water? It's going to go up until they reach equilibrium. What happens to the average speed of the aluminum? It's going to go down. Good? Makes sense? All right, that's it for today. You can work on